Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist, the place where you know how to learn chemistry for the chemist. All right, so here we go. We're going to continue on with our electrons and atoms worksheet. And just so that you know, we have done a number of things. We have done a video, I have done a video rather, that is on quantum numbers on the periodic table, which covers what you see right here and more, of course. And then we have done a number of other things related to this. So the first video covered the problems 1 through 10. If you were given a set of quantum numbers, then you should be able to identify the element if this is the quantum numbers for the last electron in that element. Then the next part was identifying the set of quantum numbers as well as valence and core electrons for a particular element using the last electron. Then the next set was to derive a set of quantum numbers like what you see here if I have given an orbital box diagram and then circled electrons. All right, perfect. So now what we're going to do is we are going to do the next step. And the next step is to do the following. We are going to write out orbital box diagrams and electron configurations of the said elements. So before we get moving on that, what we really need to do is label a periodic table. Okay, so let's do that first. We're going to label the periodic table. We're going to highlight some sections on the periodic table. And then from that, we're going to derive our different types of orbitals and what we need, right? So let's do that right now. Let's pull out a wonderful periodic table, and we're going to make use of it here very soon. And we're going to start off with a brand new periodic table here. And let's see what we got. If we can fit this all here on one screen. Perfect. All right. So the colors mean nothing. They just are to identify sections on the periodic table here. So you could choose any colors if you want to, that is. These are S-type orbitals. That does include helium. Helium is an S-type orbital. So that goes right over there. Okay, the next one here is going to be right here in this section right here. And it does continue here for these elements, which I don't have on this periodic table, but these are P-type orbitals. Okay, and then the next section on our periodic table is right here, and that goes like this and like that. And here we go. In that section, these are D-type orbitals. And finally, what we have is on the bottom of the periodic table, and right here, these are going to be F-type orbitals. That's an F. Okay, so what we need to do is label the numbers that are associated with these here. And these numbers go hand in hand with where they're located on the periodic table. So I'm going to write these in red. Hopefully you can see red, and hopefully that's okay. So here we go. N of 1, N of 2, N of 3, N of 4, N of 5, N of 6, N of 7. Okay, the D's are 1 less than the period. So that means that this is going to be a 3D instead of a 4. This is 5, so the D's are 1 less than that. That's a 4. This is a 6, period 6. That means this is a 5. And this is period 7. That means that this is a 6. Since the F's have been inserted into this line right here, that means that they are 1 less than the D's. So this is a 4F and this is a 5F. All right. So we're going to be referring back to this periodic table right here in order to do this worksheet. So hopefully that makes sense. And so we're going to start off with our first one here. And our first one is right here, and that is going to be nitrogen. Okay, so zooming on in this periodic table as tight as we can make it. Okay, let's put our little weights on there. Perfect. Good deal. We are there. Okay, so the first one is right here. And so I'm going to give you just the top of this worksheet here. Here we go. Perfect. The first one is nitrogen. Okay, and so what we need to do is we need to find nitrogen on the periodic table. Here is nitrogen right here. Okay, so I'm hoping that you notice that this is part of that ASZ notation, which is standard nuclear notation. That 7 there on that is the Z. That allows you to find the element rather quickly. So you're going to find element number 7. That's element number 7. That's right there. Okay, we're going to use the noble gas notation here to get the electron configuration, and then I'm going to do the orbital box diagram after that. I know this just says the orbital box diagram, but for some people it will be easier if you write out the electron configuration first and then the orbital box diagram. That will be most helpful. So let's start off with nitrogen, the noble gas that is prior to it. That's one period up and off to the right, helium. So we're going to write helium in brackets. That's why this brackets is right there, and that is for helium. Then that counts up to number 2. Then it's going to be 3 and 4, and that's energy level of 2. That's 2, and that's an S-type orbital, right? As we have labeled right here, S. And so that's an S-type orbital, and there's 1, 2, and so that's 2s2. Now there's a break right here, and the S's and the P's go in the same number, right? There's the same horizontal section, as you can see. So 2, and so this is 2. So this is what type of orbital? This is a P-type orbital. So this is a P, and then it's 1, 2, 3. So there we go. So how you label these boxes is as follows. We've already got the helium there for the noble gas, and then we're going to have 2s. There's no number up here, so I want to make that perfectly clear that there's no number up here, and then we're going to have the 2p, just like we're doing here. So we're going to emulate and simulate what we've done here. We're going to use this as a reference. There's 2 electrons. The first electron, always, all the time, is an up arrow. That's how these electrons work all the time. So this is an up. The second electron in the box is down. This is following all the rules. That is the Aufbau principle. That's the order of energy filling, Pauli exclusion principle, and Hund's rule. And that is maximum number of paired electrons, and the every single electron can have a different set of 4 quantum numbers. Then we're going to have 2p3. So that's going to be up, and then up. And then there'll be some other questions that will follow on based on these orbital box diagrams of which we have done here. So that is it for nitrogen. We're going to do the next element here, and that is element number 16, which is sulfur. So that's element number 16, that's sulfur. So I'm going to peel this down. I'm going to find number 16. Okay, the noble gas that is prior to element 16 is going up and over, and so that will be neon. So I'm going to write Ne, that will be brackets, and then that is counting up to 10. So the next number is 11 and 12. That's a 3. That's the energy level of 3, and that is an S-type orbital. So let me peel that back there. That's an S-type orbital. So that's an S-type orbital, and that's 1 and 2. That's 2. And then it's in the same horizontal, same energy level, and so that is a 3. This is a P, so I'm going to peel that back, and that's a P right there. So this is P, and that is 1, 2, 3, 4. So that's 3p4. Again, we're going to label this here. This is a 3s type orbital and a 3p type orbital, and it's neon as the noble gas, and it's 2 electrons. That's first up, then down. Those are anti-parallel spins. Then there are 4 electrons. It goes 1, 2, 3, and 4 in that order. So hopefully that makes sense for you. Okay, perfect. All right, and the next element is right here, and that is element number 23, and that is vanadium. So I'm going to scoot this periodic table up a little bit so that we can see just what we are interested in here in our worksheet. So that's at number 23, which is right here. That's vanadium. Okay, so I am going to go up 1 period and slam it far to the right. That is going to be argon. So that's Ar, that is the noble gas. And then that is counting up to 18. So 19 and 20 is 4, and it's a type of orbital of S, and it's a 1, 2. So that's 4s2. And then it's a 3. So note note 3. It's a 3. It's a 3, and it's a D type. So pull this back, and that is a D in that section. That's a 3D, and it's a 1, a 2, and a 3 to get to that element, 3D3. And so this is going to be AR right there like that. This is labeled as 4S. This is 3D. And then there are 2 electrons in the 4S. That's an up, and then that's a down. And then there are 3 electrons in the 3D. That's an up, that's an up, and that's an up, just like that. Okay, perfect. Hopefully that's working well for you. I want you to make sure that you most certainly need to have the periodic table labeled just like this, or have it memorized so that you understand that. This is hard to see. This is actually an F right there. This is a D, this is a P, and this is an S. Okay, so hopefully that makes sense. And then these numbers here on the far left-hand side, these are the principal quantum number for that energy level. And the Ds are 1 less than the period. The Fs are 1 less than the Ds, or 2 less than the period, either or, however you look at that. Okay, so let's work on our next element here. Hold on just a second. All right, so let's do the next one, which is going to be nickel. All right, so here is nickel. Just a quick little advertisement break here, and you are watching videos from the Crazy Hat Chemist. That's right, folks, the Crazy Hat Chemist. And this is where you learn real, actual chemistry so that you can be successful. Here we go. So the next one is going to be nickel, and that is element number 28. Nickel is element number 28. So let's find nickel. Here's element number 28. That's nickel. So what we're going to do is go up 1 period and slam it to the right. That is argon. So I am going to write AR in brackets, and that is the noble gas that's associated with argon. And so that's counting up to 18. So 19 and 20, it's 4s1 and 2. So 4s2, 4s and 2, just like that. And then this is 3D, 3D, 1, 2, 3, 4, 5, 6, 7, 8, 3D8, 3D8, just like that. So now what we need to do is copy the same thing. We have argon right there like that. This is 4s. This is 3D. This is 4s2. So that's an up and that's a down. And this is 3D 8. So it's going to be 1, 2, 3, 4, 5, 6, 7, and 8, just like that. Okay. So just to make sure that you understand something here, the reason that this electron here, this second electron in each box is down as opposed to up is because the first electron is up. The second electron must have a set of 4 quantum numbers that is different. So this is called the Pauli exclusion principle. The Pauli exclusion principle states that every electron in an atom must have a different set of 4 quantum numbers. So, for example, both of these electrons have an N of 4. Both of these electrons have an L of 0. Both of these electrons have an M sub L of 0. Where they differ is their M sub S value, and this satisfies the Pauli exclusion principle, meaning the M sub S of this electron is a plus 1/2, the M sub S of this electron is a minus 1/2. Okay, making sure you understand that. The next rule is Hund's rule. Hund's rule says maximum multiplicity or maximum number of parallel spins. And this is why the first electron is here and the second electron is in this box and not in this box down. And the third electron is in the next box. This is maximum multiplicity. This is maximum number of parallel spins. So that's very, very important here. This is Hund's rule right here. The Aufbau principle is stating that you need to fill in the 2s orbital before you fill in the 2p orbital, which of course is going to be before the 3s of any kind. And the 1s are already filled in first. Okay, perfect. That's following those rules. So the next number that we are going to do is number 27, which is right here. and this is going to be the element of copper, and that is Cu, and that's element number 29. So let's find number 29. Here's number 29. It's just one away from nickel. So I'm going to go up one period and slam it to the far right to find that noble gas that I'm interested in, and that is argon. That's going to be in brackets. Then it's going to be a 4 and an S and a 1 and a 2. A 4 and an S and a 2. And it's going to be a 3, a D-type orbital, and then 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 3D9. So you're going to find AR in brackets. That's the noble gas. This is a 4S type orbital and a 3D type orbital. I'm going to have an up, then a down. Then I'm going to have an up, and an up, and an up, and an up, and an up. By the way, this is Hund's rule right here. Maximum multiplicity, maximum number of parallel spins. The next electron is going to be down, 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 and then finally down. Okay, I want to let you know that this is the predicted electron configuration and orbital box diagram of copper right here. It's not the actual. So the actual is actually different, actually. Okay, but that's for another year of chemistry. All right, so we're going to do the next element here, and that is selenium. That's element number 34. So I'm going to find 34 on my periodic table. That is right there, just like. All right, so we're going to find. So let's find that selenium one more time again. There's element number 34. That's selenium right here. We're going to go up one period and slam it to the far right. That's argon. So we're going to say AR in brackets. That's going to be for our noble gas electron configuration. Then it's going to be 4s12. That's 4s2. Then it's going to be 3d. 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I'm going to put that right. Okay, so that is a 3D10 that we did. And then our next one here is right here. So this is in the P's. This is a 4P, 1, 2, 3, 4. 4P4. I want you to notice something, that the S's and the P's stay with the period, okay? All right, fantastic. So let's do this orbital box diagram now that we have this electron configuration nailed down very nicely. Okay, so we're going to first label these boxes. That's 4S, that is 3D, and this is 4P. This is AR. Now, one other thing that I'm going to mention right now is that the number of boxes is critical. So before you label these boxes here as 4S and 3D and 4P, you need to make sure that these labels are appropriate for the number of boxes. So the S-type orbitals only have one box. The P's always have 3. The D's always have 5, and the F's will have 7. So you need to count the number of boxes before you label them, before you put those electrons there, just to be sure. So the 4s2, it's going to be up, then down. Then the 3d is going to be 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it's 4p4. That's 1, 2, 3. This is also an example of Hund's rule. That's maximum multiplicity right here. And the final electron is going to go right here, and that is like that. And this is an example of the Pauli exclusion principle. These two electrons have the same set of 4 quantum numbers, except for the very last m sub s value. This is positive 1/2, this is negative 1/2. All right, cool. Let's do the next element here, and that will be, which one? Here it is, right here. That is bromine number 35. So I'm going to pull this down for a bit here, and I'm going to do bromine, and that's element number 35. So I'm going to go up one period and slam it to the right, so that's argon. So I'm going to write that down, AR in brackets. I can fill that in, AR in brackets there. Okay, then that will be a 4s12. I'll write that down, 4s2. Then it will be a 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's 3D 10. And then it is in the P's, and the P's stay with the period. That's 4. So 4P, 1, 2, 3, 4, 5. 4P and 5. It's just one electron beyond selenium, that which we just did. So let's simulate the same thing. Remember, before we label these boxes, S's only have one box. So that's why I know this is a 4S box. This has 1, 2, 3, 4, 5 boxes. So it must be a D, and it happens to be a 3D. This has 3 boxes, so it must be a P, and that is a 4P. So I'm going to place these electrons. That is 1 and 2. This has 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this has 5. That's 1, 2, 3, 4, and 5. Just like that. Perfect. All right. Next element that we're doing here is rhodium, and that is element number 45. So element number 45. So let's find element number 45. There's 45, there's rhodium. So what we're going to do is we're going to go up one period and slam it to the right, and it's going to be krypton. So that's going to be my noble gas. I'm going to write Kr in brackets, just like that. So that's element number 36. I'm going to do 37 and 38. That's going to be a 5s12, just like that. Okay, so we got krypton, and we said that that's going to be a 5s2. So let's write that down. That's 5s2, just like that. All right. And then we're going to get to rhodium. It's a 4, it's a D, and it's 1, 2, 3, 4, 5, 6, and 7. So 4D and 7. Perfect, just like that. So now what we're going to do is we're going to write krypton right there like that. This is going to be labeled as a 5S, and this is a 4D. Okay, I know this is an S because there's a single box. This is a D because there's 1, 2, 3, 4, 5 boxes. 5S2, that's an up, that's a down. Okay, 4D7, 7, 1, 2, 3, 4, 5, 6, and 7. Perfect. All right. The next one is lanthium. That is element number 57, lanthium. Okay. So lanthium is element number 57. So let's find number 57. So 57 is right here. Okay, number 57. So I'm going to go up one period and slam it to the far right. That's going to be xenon. So xenon now is my noble gas of interest. That's going to be in brackets. That's counting up to 54 immediately. Then I'm going to count up to 55 and 56. That will be 6 and an S and a 1, 2. So 6s2, 6s2, just like that. And then it's going to be this next one here, and that's a 5D. Remember, the D's are one less than the period, so this is a 5D. So it's a 5D, 1, and then I'm at that element. So that's 5D1. Again, labeling, this is xenon for my noble gas. This should be a 6s. This should be a 5D. S's have a single box. D's have 5 boxes. Notice that I do not have the electron configuration written here. That is, there's no number here, there's no number here, no number here, no number here. It's just the labeling of the energy level and the orbital type. Energy level and orbital type, not the number of electrons. The number of electrons is assumed within this orbital box diagram as arrows. And then we have this just like that. So it's 6s12 and 5d1. Perfect. Done. Beautiful. Looking good. Now let's do the next one. The next one is element number 79, which is gold. So let's see if we can figure out that one. So gold is right here. That's element number 79. That's AU. We're going to go up one period, slam it to the right. That's xenon. So we have xenon in brackets, just like that. Okay, and then that's up to element number 54. So we're going to do 55 and 56. That's a 6 and an S and a 1, 2. So 6s2, 6s2. Okay, Then after that, it is going to be a 5D, so that's 5D1. That gets me to 57. Okay, so that's a 5D1. How we do this is we only count one number at a time. The next number is 58, so I'm going to have to come way down over here, and this is going to be a 4F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's 4F14. 4F14. Now, that only gets me up to 71. So now I'm going to do 72. Now, I've already done one of the 5Ds, and that's why it's 5D1. So 5D1, 2, 3, 4, 5, 6, 7, 8, and 9. So 5D9. So I'm going to change this 1 into a 9. You cannot separate them out. You must have them together. Now, labeling these boxes here, let's label that noble gas as xenon. This is a 6S because it has a single box. I need to count these boxes and figure out which set of boxes these are. Is this a D or is this an F? Is this a D or is this an F? Is this a D or is that an F? That's the question. And the number of boxes tells you what type of orbital it is. So remember, as we have done before, if we look here at the top here, 3 boxes are P's, 5 boxes are D's, 1 box is S. So 1 S, 3 P, 5 D, 7 for the F's. 1, 2, 3, 4, 5, 6, 7. So this is going to be 4F. 1, 2, 3, 4, 5. This is a 5D. All right, so it's 6S2, that's an up, that's a down, then it's a 5D9, that's 1, 2, 3, 4, 5, 6, 7, 8, and 9, and then 4F14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Perfect. All right, we only have 2 more here to go. Remember, just a quick little advertisement, self-advertisement. We are watching the Crazy Hack Chemist. It's all your chemistry needs are right here and meant right here because this is where you learn chemistry for real. Okay, the next element here is element number 97, and that's a berkelium. Okay, so let's find that element here. Okay, so berkelium, let's try this again. Here's element number 97, that's berkelium. Where does this go? This goes right here, right here. So we're going to go up 1 period and slam it to the right. That's radon. So Rn number 86. So it's going to be Rn in brackets, Rn, and then that is 86. So after 86, I'm going to do 87 and 88. That's a 7 and an S and a 1, 2. So 7S2, write that down. That's 7S2. Then what we have is a 6D1. That's this element right here. That's 6D1. 6D1. And then that is 89. 90 is right here. That's a 5F. 5 and F. So 5F 1, 2, 3, 4, 5, 6, 7, and 8. 5F8. 5F8. And again, what we need to do is count the boxes. S orbitals have 1 box. This is a 7S. F, S orbitals have 1 box. F orbitals have 7 boxes. 1, 2, 3, 4, 5, 6, 7. So this is 5F. And D orbitals have 5. 1, 2, 3, 4, 5. So that's a 6D. So this is 7S1 and 2, and this is an F, so it has 8. That's 1, 2, 3, 4, 5, 6, 7, and finally 8, and a 6D1. That goes right there like that. Perfect. All right, we have 1 more here to do on this here, and this is hassium, and this is element number 108. So let's find this element here, number 108. That's right here, number 108. So we're going to go up 1 period, slam it to the right. There's my noble gas of Rn. And we're going to put this down below here. So Rn in brackets. I'm going to put that Rn in brackets right there. That has enabled me to count up to 86. Then I'm going to have 87 and 88. That's a 7 and an S and a 1, 2. So 7S2. Write that down. 7S2. Okay, then I'm going to have a 6D1. That's this one right here. That's a 6, that's a D, that's a 1. 6D1. The next element that's after that 89 is 90, and that's going to be a 5F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 5F14, 5F14. And then I've already done 61, 62, 63, 64, 65, 66, 6D6, 6D6. I'm going to change this 1 to a 6. Now I'm going to do the orbital box diagram of this same thing. Let's label it. This is a 7s. This has 7 boxes, so it's a 5F. This has 5 boxes, so it's a 6D. And the 7s is an up and a down, that's 2. And a 6D6, so 1, 2, 3, 4, 5, and 6. And then it's 5F14. So these are all filled in. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and finally 14. Okay, now we think that we're done with this part. We are. But now what we're going to do is we're going to do one more little tiny thing. And that one more little tiny thing is we are going to answer question number 35. So question number 35 says how many unpaired electrons are in each of the elements, and we're going to see problems 23 through 34. So this is 23 and 25. So what we're going to do is we're going to figure out the number of unpaired electrons. So I'm going to highlight the unpaired electrons in orange in each of these cases. So for nitrogen, unpaired electrons, that's 1, 2, and 3. So I'm going to place a 3 right here like this. So in order to get the number of unpaired electrons, it's easiest to find the orbital box diagram, although you can do it in other ways. I'm going to follow the orbital box diagram, of which we have already written, and that will make it easiest. Number of unpaired electrons in sulfur, that's 1 and 2. Okay, so this is 2 right there like that. Number of unpaired electrons in vanadium, 1, 2, and 3. So that is a 3 there like that. Okay, number of unpaired electrons in nickel, that's 1 and 2. And so that would be 2 for nickel. Okay, so by the way, these, if it has a single unpaired electron, it's paramagnetic. If it is paramagnetic, it's held up in a magnetic field. So paramagnetic has at least one, if not more, unpaired electrons. Let's do the rest of these with copper. Copper, there's one unpaired electron, and that's a 1 right there like that. How many unpaired electrons in selenium? 1 and 2. So this is going to be a 2, just like that. Okay. And then let's continue on this little journey. How many unpaired electrons in bromine? 1 unpaired electron in bromine. 1 unpaired electron in bromine. How many unpaired electrons in rhodium? 1, 2, and 3. So there are 3 unpaired electrons in rhodium. How many unpaired electrons in lanthanum? 1 unpaired electron in lanthanum. That's 1. How many unpaired electrons in gold? 1 unpaired electron in gold. 1 unpaired electron in gold. How many unpaired electrons in berkelium? 1, 2, 3, 4, 5, 6, and 7 unpaired electrons. 7 unpaired electrons in berkelium. How many unpaired electrons in hassium? Hassium has 1, 2, 3, and 4 unpaired electrons in hassium. That's 4 unpaired electrons. So hopefully you see how you get the unpaired electrons as well as the orbital box diagram. Absolutely critical on that. Okay, so where do you have diamagnetism on the periodic table? So that's an entirely different question here. So where are the elements diamagnetic? That means that they are held up in a magnetic field. So diamagnetism, those diamagnetism. So if they're diamagnetic, they would rather die than being held in a magnetic field, so they will fall on through. Paramagnetism has unpaired electrons and they will be hung up. So these are paramagnetic. What are diamagnetic elements? They have paired electrons all the time. So everything here is paramagnetic, okay? As well as this group here is paramagnetic, as well as these are paramagnetic. So those are paramagnetic. So those elements that I've highlighted in, the elements that I've highlighted in orange right now, these ones are going to be diamagnetic. So diamagnetic has those paired electrons. These are diamagnetic. In orange are diamagnetic. Paramagnetism has unpaired electrons. All right. Hopefully that worked out well for you. I hope you have a great day, and I'll talk to you later. Bye for now.